Welcome to my mini lecture Tomography 204. In this video I will discuss the structure of tomographic matrices. Let's start with the 2x2 pixel model from my video Tomography 202. There are 4 pixels and 4 measured X-rays, so the size of the matrix A is 4x4. The first row of A concerns the measurement M1. The first element of the first row describes how long does the X-ray travel inside pixel number 1. And note, we take the pixel width to be 1. The same ray travels also through pixel 3, so we can insert another unit element into A. This ray doesn't pass through pixels 2 and 4 at all, so we put zeros in the corresponding matrix elements. Now the first row is complete. We can build the remaining rows in the same way. This is actually the matrix we saw already in video Tomography 202. Here's a bit more complicated case. The unknown has 3x3 pixels now, and there are 6 X-rays measured. A question to you: how many rows and columns do you think the matrix A should have? You can pause the video here for a while if you want to think about it. Okay, the pause is over. Time for a spoiler. The matrix A has 6 rows, 1 for each X-ray we measure. Also, A has 9 columns, 1 for each pixel. Now I have a homework assignment for you. Fill in the actual matrix elements to A, assuming that the pixel width is equal to 1. Note that the slanted X-rays travel in this example exactly through the corners of some pixels. So you will need some algebra to find out some of the path lengths of X-rays inside pixels. I will reveal the solution in the end of this video. Let's study a bit more complicated example. Recall the tomography problem from my video Tomography 203. There we had 12x12 pixels numbered from 1 to 144 in this column-wise manner. We have 11 measurement directions and 21 X-rays for each direction. Every X-ray corresponds to 1 row in the matrix. Therefore, our system matrix A has 11 times 21 equals 231 rows. Next we see how all the non-zero elements of the matrix A are distributed. Note that the matrix will have 11 blocks of size 21 by 144, 1 for each direction of X-rays. The first X-ray direction is aligned with the pixel rows. Note that the 5 first rays travel outside of our target model. Assuming that the pixel width is 1, we would get similarly 0 or 1 entries, as we did in the 4x4 matrix before. The first 5 rows are purely zeros, as the first 5 rays do not touch the grid at all. However, MATLAB does not assume infinitely thin X-rays. Rather, it uses a pencil beam model where rays have a finite width. So we get fractional matrix elements slightly spread out compared to the thin ray approach. This is similar to the anti-aliasing technique used in computer graphics. After pixels x1, x2 and x3 and so on, the next non-trivial part of matrix A is related to pixels x13, x14 and x15. Here are the matrix elements. And now the whole block corresponding to direction 1 looks like this. The block has mostly 0 entries, and the non-zero elements shown in blue form specific patterns. Moving on to direction 2, where the X-rays travel at an angle of 32.7 degrees. The rays are numbered from 22 to 42. We see that ray number 24 does not touch the grid at all, but ray 25 already does. When we look at the corresponding elements of A, we see that ray 24 is again thicker than just a line, since it has a positive entry corresponding to pixel X1. Filling in all elements from direction 2 leads to another block in the matrix A. And when we use all the 11 directions, the matrix A gets completed one block at a time. In case you're wondering, I did not build this A matrix for the 12 by 12 pixel case by hand. That would be such a tedious task that I wouldn't really recommend that to anyone. In the next video, Tomography 205, I will show how I programmed the calculation of the matrix A. Amusingly, the way I did it is based on a matrix-free approach to tomography. See you in the next video. As the first 5